Welcome to this video on sampling distributions of the mean and using the central limit theorem to understand a statistical analysis more broadly. So I want to start off this video by looking at a specific example that will help us build an intuition as to what sampling distributions of the mean means. So consider an island with 2,287 residents. The age of the islanders is summarized by the mean of them being 26.42 years old and the standard deviation being 25.65 years. And if we were to graph a histogram of the age of the islanders and how many people have that age, it would look a little bit like this. So it's very much right skewed and centered at a young population. And yeah, this is a histogram of these 2,287 residents and their ages. Okay, so what is a sample? Well, a sample is taking a group of islanders randomly from the 2,287 residents. So that could be one islander, or that could be all of them. And if we were to take a sample, we can calculate the mean of that sample. So we might take a sample of 25 people, just randomly pick 25 off the island, and then we could work out the average age of those people and have a sample mean x bar and a sample standard deviation s, which is giving us descriptive statistics of this sample. So if we were to do this repeatedly, every time we'd expect to get a slightly different answer, because of course when you pick randomly from this population, you could pick someone who's quite old, you could pick someone who's really young, you could pick anyone in the middle, and every time you do it, you can pick a different group of 25 people, and that would give you a different take on the mean and the sample standard deviation of that group. But if we were to do this 20 times, so randomly choose 25 people, calculate the mean, put them back, shuffle, pick again, we would have a sample of sample means. So looking at this box here, this is a computer generated repicking of this population here and working out the average of those people. And we've got here quite a disparity amongst these averages. Here there's one as young as 15.5 as the average mean, and then there's older ones like 35.6 and 33.6 that comes up twice, 38.6 probably the oldest. And yeah, this is now a distribution of sample means where we have actually a distribution in of itself from all the sample means that have been created here. And then we could start to graph the distribution of sample means. And now this histogram here is telling us every time we calculate this sample mean, this is how frequent it occurred. So the sample mean distribution is centered towards, I guess, 25 maybe, and is looking fairly spread out and flat in this distribution. So what does this depend on? Well, it depends on the mean and variance of the original distribution. It depends on how many times you take that sample of sample means. So in this case, we took it only 20 times, but if you took it 1,000 times, it'd look a bit different. And yeah, it especially depends on how many people are within every sample. Like if you took a sample with 2,287 people, then you'd always have the exact same mean, which is 26.42. And so how many people you take per sample will also quite heavily affect what this distribution looks like. And what you'll actually find is that there's a trend for this distribution. Here are 3 histograms that depict that trend. So let's say we took 1,000 sample means, and what is varying in this histogram is how many people are in each of those 1000 samples. So here, every sample contains only 4 people, and that will give us a histogram that looks like this. You'll notice that it is looking a little bit like the actual population mean itself, but then slightly shifted away, especially as you have 4 people. If you were to take exactly one person, you would expect it to look just like this. But as we're taking 4, you can see it's still centered very much to the left there, but looking a bit like this. Okay, there's the sample standard deviation and the sample mean. The mean of the sample means and this sample standard deviation for the whole distribution. Okay, here we can change n to 16. So now every sample has 16 people in it. We get a very similar mean and a sample standard deviation that is smaller for the whole distribution. And then this third one, when n is 100, we get something that looks like this. We get a very similar mean again, but our standard deviation of this distribution is once again smaller. And the overall trend that we have from our distribution of sample means is that the expected value of this distribution is the original mean, and that the standard deviation of this distribution is the standard deviation of the original distribution divided by the square root of n. So that makes the expected value of our sample means unbiased and a standard deviation limiting towards 0 as n goes towards infinity. And what you'll see is that this makes a lot of sense because if n was equal to the population, as I said before, your sample mean will just equal the population mean and your standard deviation will be 0. And if you're only picking one person, then you will have a very high standard deviation, as you could pick anywhere across this histogram. And we can actually back up this idea here by rigorously proving that this is true. So if we look here, this is a proof to show that the expected value of the sample mean the mean of the sample means is equal to the mean of the distribution. So let's look at it line by line. The expected value of the sample mean is equal to the expected value of just plugging in what the sample mean is. And in this case, it's adding up every random variable that you have collected and then dividing by n. So if we're looking at population ages, then you might have the age of a 13-year-old, a 42-year-old, a 57-year-old, and then you add all those ages together and then you divide by how many people there are. Okay, and that is going to be the same as 1 on n being factored out of that sum, and then the sum remaining like this. And then here we can remove the 1 on n from the whole expectation because it is not a random variable, it's a constant. And then we can put the expectation inside of the sum, and then we need to sum up the expectation of every random variable. And then the expectation of any of these random variables is just mu. And this is happening n times. So we end up getting 1 on n multiplied by n times mu, which is just mu. So when you take a sample and you calculate the mean, we would expect that mean to have a average of mu. We would expect that mean to be the population mean. Okay, similarly, if we look at the sample standard deviation, we're trying to calculate the variance of our sample mean. Well, the variance is equal to this, which is just adding up. This is the definition of a sample mean. X bar is defined as this. And once again, we can factor out the 1 on n. And then in removing the 1 on n from the variance, we need to use our variance rule, which has 1 on n squared when you take a constant outside of it. And then we can add the variance of every random variable itself. And then the variance of these random variables is sigma squared, which is happening n times. So we get 1 on n squared and sigma squared. So there are n of these. And then that's sigma squared on n. And so the sample standard deviation, which is the square root of that, is just going to equal this. Okay. Now the central limit theorem is a way of formalizing what we have been talking about. And it is talking about how you should expect these histograms to look as the number of people in your sample increases. And the punchline is that it looks more and more normal, that the distribution of the means approximates a normal distribution as n gets large. So central limit theorem says this: if x1, x2, all the way through to xn are random variables drawn from a population with overall mean mu and finite variance sigma squared, and if xn bar is the sample mean of the first n samples, then the limiting form of the distribution z equal to this is a standard normal distribution. That is, the distribution of sample means becomes normal as n gets large, regardless of the original distribution of x. So this is often something that people find confusing, is that x need not be normal for the distribution of means to be normal. That's what makes central limit theorem so useful. And we can therefore approximate the distribution of sample means using a normal distribution. Of course, this is talking about the limit. So when n is not arriving towards infinity, heading towards infinity, it's not necessarily exactly equal to a normal distribution, but it will approximately be normal. And the larger your sample is, the better this approximation is going to be. And in practice, n being greater or equal to 30 can be a nice rule of thumb to have a distribution that is normal enough to use statistical analysis on it. That's a very crude estimate. Okay, now this description here is talking about our distribution of the means, and the idea is that this is a distribution of mean that could be anything, but as the limit goes to infinity, the distribution is specifically normal, which is just said here. So the theorem is not specially saying like some formula or rule or the distribution is equal to this. It's just saying you could mathematically describe it in this way, but what distribution that is could be anything. And the central limit theorem says that as n goes to infinity, this distribution is normal. That's how you interpret this part here. Okay, just to finish here, we often see in the real world things are distributed normally. And why is this the case? If you understand the normal distribution, it has a very complicated probability density function, which has exponentials, pi, squares in the exponents, etc. So why is it that so many things in practice follow the normal distribution? And the reason for it, here's the probability density function of a normal distribution, which is quite hectic. So how do so many natural things have a probability density function that actually looks like this? And the answer to that is because most of these cases here, what determines your height or your grades or someone's IQ or their blood pressure are factors that are coming from the average of something. And the thing is averaging might not be normally distributed, but because it is an average, using the central limit theorem, it is creating a distribution of sample means that is average. So your height, which is influenced by multiple genetic considerations, if it's averaging across those considerations, then even though any one of those factors might not be normally distributed, the average is, and that's what makes your overall height normally distributed. Likewise for your grades or for your IQ or your blood pressure. So this is what allows the central limit theorem to be so prominent, is that anything that ends up being the average of averages is fair game to be impacted by the central limit theorem and becoming a normal distribution. Okay, I hope you found this overview of sampling distributions of the mean and the central limit theorem helpful. Thank you for watching.